have linear power supplies, which that's all you used to have, pretty much, in the old days. And they more modern linear supplies, they use an integrated circuit as a voltage regulator, normally like a 3-pin device, kind of looks like a transistor. And it will, in most cases, they're fixed. They'll regulate to 12 volts or 9 volts or 5. You can buy them for quite a variety. There's a few that are adjustable, have another input, and you can control the output voltage with a different reference. But essentially, it's a reference carrying the input voltage to the regulator and controlling the current through a path transistor to maintain the output voltage with both. Kind of a typical circuit of what would be in one. You could actually implement it with separate components for the transistor and the zener diode. In this case, Q1 is what's called a path transistor. That's what you control to control the current from collector to emitter to load. And that allows you to keep the constant voltage on the output. And the zener diode is the reference source that it's comparing against. So that's how it regulates to a particular voltage. C2 is just a filter capacitor so that this reference voltage looks like it's a constant DC source. You don't see any ripple because your input voltage here may not be a nice constant 25 volts. I mean, it could be varied or have some noise on it. So you want this reference voltage to be as good DC as you can get. So that's the whole purpose of that filter capacitor. And then, like I said, D1 to the zener diode is your voltage reference that it's using to compare the output against. What type of circuit is shown in figure E7D? How does a linear electronic voltage regulator work? Okay. How about B? You kind of need this aspect of this. So it's got to be Charlie or Delta. Is it a switching supply? So it doesn't have duty cycle. Must be Delta. What is the purpose of Q1 in the circuit? If it was a shunt regulator, it would be wrong. We didn't talk about a shunt. This is the series. That's it. How about Charlie? So the current keep the output voltage constant. have a constant voltage, depending on whatever value that zener is. That's being applied to the base of that collector transistor. So the transistor conducts current based on the amount of current between the base and the emitter. Well, that voltage difference is the difference between that 12 volt output load and the reference voltage. So if the load changes, okay, and draws more current, the load is lower resistance. Initially, if that voltage drops, then you've got a change in the bias current on the transistor, which would allow it to conduct more current because the load wants more current to bring the voltage back up. And just the opposite, if all of a sudden it goes up and you're drawing less current, that bias is going to change and reduce the amount of current through the pass transistor. So I guess in a way you could say it's negative feedback, but it's just you're changing the bias on the base emitter. I guess this controls the current. It's the thing that controls the current. What's the purpose of C2? Bias is done by D1. So all C2 is doing is filtering out any variation coming from your 25 volts. So you just want to try to make that a pure DC voltage. We've talked about D1 being a zener. We talked about zeners last week. When you reverse bias them, they will conduct at a particular voltage. They basically avalanche. So that's why it makes a very good voltage reference. So what device is used as a stable voltage reference? This is for people with short-term memory. Okay, we have two types. We have linear, which we just talked about, and in the linear, okay, we have a series and a shunt. I mentioned shunt before. The difference is the sort of pass transistor or shunt regulator is actually across the load. So the way this is very inefficient because it's absorbing the power that's not going to the load. So that Q1 transistor is always dissipating power. And it's split. It either goes to the shunt regulator or goes through the load or some portion through each one. Its advantage is looks like a constant load as far as the input. Doesn't have any negative resistance or any, which you can see when we talk about switching. So which of the following describes a three-terminal voltage regulator? Which of the following device, a linear voltage regulator operates by loading the unregulated voltage source. Dropout voltage, okay? Just because of the fact that transistors there has a bias voltage to overcome, you have what's called dropout voltage, where in order to, say, regulate to 12 volts, if the dropout voltage was 2, you'd have to have a minimum of 14 volts into the device in order to maintain 12 volt power. So it's going to be a difference between your input and output. That's what the dropout voltage minimum is. And somewhere around 1.5, 2 volts, I think, is about typical for most of the regulators. What is the dropout voltage of an analog voltage regulator? Dissipation is going to be the difference between the input and output and the current going through. So if you have that 2 volt drop at 1 amp, okay, you're going to have 2 watts being dissipated in that pass transistor, basically. So that's one of the things you have to account for, depending on how much current you're going to have, depending on what that dropout voltage is, or how large a heat sink is to dissipate that power. In that example, 2 watts would take much. If it was a PO220 package or something like that, you could probably handle it without a heat sink. But for larger power supplies, you're going to have either a very large heat sink or a smaller one with forced air, or in some cases even liquid coolant. But I don't normally see that in a power supply. Which of the following calculates power dissipated by a series linear voltage regulator? Okay, switching power supplies. I'd say most of the power supplies used in amateur radio today are probably switching power supplies. A whole lot lighter, cheaper, smaller, and most of them, they're pretty good. You get what you pay for. I don't think I'd buy off-brand Chinese one off of eBay. If you got a name brand, most of them set up so they don't really generate a lot of noise, which is one of the problems with the switching power supply. And they basically work by varying the duty cycle of the control level to give you a constant output. Like we talked about the Class D amplifier, same kind of a deal. How does the switch mode voltage regulator work? And they normally will operate at very high frequency. Components you need to filter those high frequencies out can be very small. So you don't need big toroids and capacitors, where in the linear power supply, you're trying to filter out 60 hertz. So you're talking about big components. So we talked about all the cheaper, lighter, better, may or may not generate RF noise. In some cases, I have one, I think it's an MF Malenko. It actually allows you to adjust the switching frequency. It's an there. You know, I take it from the switching type power supply, that's expensive and light. But most of the modern solid state transceivers operate on essentially 12 volts, nominal 13.8 voltage, which is the nominal voltage for a I'd say not fully charged lead acid cell, very nominal. They go up to about 14 volts, really topped up, drop up kind of rapidly. They stay at around 13.8 for quite a while, and then start dropping. If they get down to 12, it should stop, damage most of the batteries. Isn't as much of a problem with the lithium iron phosphate, but because they'll go into a deeper discharge, you have a wider operating range. Although a lot of times the radio operates, verified that on my 7300 because I read about it, and I dropped it down to 12 volts, and the power went down and spurs went up. Not sure why that happens, but it does. Because of the usually the size of the capacitors and the voltage you're talking about, you can have some very high interest currents, a high voltage supply like for power amplifier. And one of the things they do is do a what they call a step start or soft start circuit. Step start usually is like a relay or something, and it'll provide a lower voltage to start charging things up and then switch to full voltage. And a soft start gets more of a linear ramp up. And in some cases, the ones I built for my CNC milling machine, which run at about 90 volts, use varistors, which is a current variable resistor. It decreases resistance as the current goes up. So initially it's a high resistance, and then as the current increases, it decreases down to the fact that it's almost not in the circuit. So it gives you a nice control of the inrush current. This is a they say soft start, I call that a step start, where it's actually got a relay. So it charges the load up at a lower voltage and then switches the relay to the full voltage. So what's the purpose of a step start circuit in a high voltage power supply? LED, allow the filters capacitors to charge gradually. Because otherwise you could blow a fuse or circuit breaker. Then you have to get up and go do it, find a fuse. One of the things that you should have, and most decent power supplies, power amplifiers, should have leader resistors across the filter capacitors, especially in a high voltage supply, because you can have those thousands of volts stored in those capacitors for quite a while. If they're very good quality capacitors, they don't have much leakage. There's nothing else in the circuit to bleed them off. And they can retain those voltages for hours or days. So, most of them have a fairly high resistance bleed resistor, so it really doesn't have any effect in the operation, but it will bleed off the voltage and the charge off the capacitor over a period of time. Yeah, and it probably should really have an analog also, so even if you leave it turned on and plugged in, it turns it off. We'll talk about that. Last day on safety. What's the purpose of connecting equal value resistors across supply filters, capacitors connected in series? Kind of like same thing with lithium batteries, multiple cells, charge them, or even in operation, you can equalize the voltage across them with a high resistance resistor across each cell, so they equalize. And the same thing with the capacitors, because usually for high voltage, you're going to have to put them in series because each one, say maybe it's 1,000 volts, well, you need 3 or 4 of them, or 3 or 4,000 volts. Battery power. Okay, if you're planning to be remote, go out on the quota, or if you just want to be able to operate when your AC power goes away, a lot of people have a battery backup system where they can switch over and operate on the batteries, and usually they'll put up some solar cells so they can keep them charged. If you plan to do that, then there's a formula. I said there wasn't any, but I lied. Calculate how long you can operate. You know, politicians can do it. After the first one doesn't count, right? You specify how long you can operate by looking at the capacity of the battery, and it's usually in amp hours, and divide that by the average current draw for whatever you're operating. So you have to kind of estimate to figure out what that would be. it will be time in hours in this case, because you're going to divide the amp hours by number of amps. So if you were, say, drawing an average of 1 amp, you have a 12 amp hour battery, in theory, you can operate for 12 hours. Not really, because even though the battery is a lead acid battery, 12 amp hour battery may store 12 amp hours, but not at above 12 volts. So you're going to have some charge in there you can't use. So his battery operating time calculated. Technically, I didn't lie because I said you didn't have to have your calculator. Okay, so if you've got your batteries and you want to keep them charged up when you don't have power, you get a solar array, a appropriate charge controller for the type of batteries you have. It's going to be different. If you're using lead acid batteries or you're using lithium iron phosphate batteries or something else. Maybe in some cases you can find one that's switchable to do different types. But normally they're for a particular type of battery. And the main reason to have it is because you don't need to charge the battery. It's bad for both lead acid and lithium. Actually, both of them can cause explosions by overcharging them, either outgassing of the hydrogen or enough internal on the lithium to actually explode. And then if the lithium is exposed to the atmosphere where there's moisture, then it likes to catch on fire. Which is not good. So you can't put water on it. Well, you can, but it sort of helps along. Yes. So what's the purpose of an inverter connected to a solar panel?
I would say D, but I've got a question for you. What is the difference between a charge controller and a regular battery charger?
Charge controller is going to be designed to operate from the voltage of your solar array, which is up maybe 90 volts or something like that, maybe higher. Where most of your battery chargers operate off AC power.
Okay. Well, if you don't mind, one more quick question in that realm. What is the difference between a power supply, a regular, like a wall wart type power supply, and a battery charger or, say, a trickle charger?
Case of a wall wart, sort of a regulated supply, not necessarily very good, but the antenna is supposed to be regulated at 5 volts or 12 volts or 9 volts. A little bit of doubling. Whereas your triple charger is just designed to provide a slightly higher voltage than the battery, keep a little bit of charge current going. Kind of flows.
So really, there's very little difference. filtering on the trickle charger?
You don't need it. You don't really care if the voltage goes up or down a little bit. All you care about is keeping the battery topped up with some current. They're up to, 15, 16 volts.
Thank you.
Yeah, that is a big one. So, what was the answer? Because they said it.